All right, let's get started. Probably close this. So last time we finished with 4.2. I said I wasn't going to go through all the examples that he goes through in 4.2. You guys were going to go home and did that. You did that. You now understand everything, showing how an argument is invalid using interpretation, showing how a set of premises is consistent using interpretation. You know what those things mean now.
Well, we knew what they meant in chapter 3.
Oh, you already had it figured out. You didn't even need to read the chapter.
No, of course.
And one of those people has that special ability. He just sleeps next to his book and he gets it through osmosis. It's crazy. But if the information's flowing in through osmosis, that means there wasn't a lot in there. Just realize that. It's kind of insulting, but people say it to people. That's funny. Never thought about that. Okay. So, and remember 4.1, we were focusing on doing proofs with just universal quantifiers. So we did the proofs with just universal quantifiers. We stopped to talk about interpretation and what we mean by interpretation now. Now we're going back to just proofs, and the next proofs we're going to do is proofs with existential quantifiers. So 4.3, almost exactly like 4.1, except for we're talking about existential quantifiers instead of universal quantifiers. And just so you know, lectures are up to date online, so everything's on YouTube now. Anyways, so let's get into inference with existential quantifiers. Just like we had our rule for universal specification, universal generalization, we have our rule for existential specification and existential generalization. Well, this is what existential specialization is, this is what existential generalization is, and then these are the actual two rules that we use, and then we'll see examples using them, okay? So, let's make sure that these make sense. These are basically sentences meant to give you intuition for what we're doing. Here's how we do it, and then we'll see examples. So let's get the intuition as to what these are talking about. So, the assertion that there is something that satisfies a given condition implies the assertion that this given condition is satisfied by some individual. If there exists something such that some condition is true, then there's a particular individual where that thing is true, right? You might feel like I'm saying the exact same thing two different ways. If that's how it feels, good. And you'll see in an example how we use that. Existential generalization is kind of like the converse of that. The assertion that a condition is satisfied by a named individual implies the assertion that the condition is satisfied by some individual. So if we know what's true for a particular individual, we know it's true for an arbitrary individual. And vice versa, if we know it's true for an arbitrary individual, we know it's true for a particular individual. Right? Okay. So our rules for existential specification, we'll start with that one. Existential specification is going from, we know that there's some individual that satisfies this condition to this particular individual satisfies this condition. That's how existential specification is going to work. So if a formula S results from a formula R, so R implies S, if a formula S results from a formula R by substituting for every free occurrence of a variable X in R, an ambiguous name, you're going to notice that we use Greek letters as a general rule for these. Yeah, that's an alpha. Sorry, I should have finished saying that. So we're going to use alphas for our ambiguous names. Our ambiguous names are going to be the particular individual that satisfies the condition. So let's restart. If a formula S results from a formula R by substituting for every free occurrence of a variable X in R, an ambiguous name, alpha, which has not previously been used in the derivation, then S is derivable from, there exists X such that R.
So X is...
Let me just give you a really small example right out the door. If I know that there exists X such that Rx, you with me? Then I can say R of alpha. That's in short what it's saying.
Because X is the ambiguous and alpha is the specific.
This is the ambiguous name, which is referencing the particular thing that satisfies the condition. So up here we're just saying there's something such that there's some X such that Rx, and now we're saying alpha is a thing such that R alpha. You see the difference there?
makes sense why they use it.
Okay, so let's read this one more time and see that that's exactly what it's talking about. Let's not use an R here. We'll just say A, and then we'll say A of alpha. So this part right here is going to be R without the this, and this part right here is going to be S. So this is S, and this is R with our definition, R without the existential quantifier. So here's the R and the S as an example for what this definition is saying, and let's go over it again. Or not definition, rule. So if a formula S results from a formula R by substituting for every free occurrence of a variable x in R, notice we don't include the existential quantifier, so x is a free variable. Good?
Mm-hmm.
So here's R, x is sorry, where were we? By substituting for every free occurrence of a variable x in R, an ambiguous name alpha, which has not previously been used in the derivation. In other words, we haven't said alpha is something else already. Good? So some alpha which has not previously been used in the derivation, then S, this, is derivable from there exists x such that R, or this. You follow that? Okay. And then this one's going to tell us that we can do the reverse. We can go from this to this. So let's look at that one. If a formula S, I think in this case we're going to switch these. R, S. So I think we're going to switch our naming for this rule. If a formula S results from a formula R by substituting a variable x for every occurrence of an ambiguous name or constant, in this case it's alpha, for every ambiguous name or constant alpha in R, then we can conclude that there exists x such that x from R.
Why is it important to go from specific to a generalization?
So let me give you an example. Say I want to see if the statement there exists x, and we'll think about talking about the positive integers. Can I say there exists x such that x is even and x is prime? Oops. Is this statement true?
Mm-hmm.
Does there exist some x,
Yes.
some positive integer such that x is even and x is prime?
Yes.
Yes, 2. So since I know that 2 is even and 2 is prime, the second rule says if I replace every occurrence of, in this case a non-ambiguous name, it's a constant, if I replace every occurrence of a constant with some variable x, I can then conclude this from this. So since I knew this, I now know this. This is how I would prove this statement true. Does that make sense using this?
Yes.
Okay. Alright, so let's just do a bunch of examples to get a feel for this, and then we'll continue. Alright, example, all humans are mortal. I'm going to try this out as we go. So 1, all humans are mortal. What's that saying? That's saying for all x, human applying to x implies mortal applies to x. Sorry, that's an x on alpha. Right?
Yeah.
Everyone follow that?
Mm-hmm.
Next sentence says, there are humans. What does that mean?
There exists human.
There exists x such that human applies to x. Good?
Mm-hmm.
And then what do we want to conclude? Therefore, there are mortals. So we're trying to conclude that there are mortals. In short, the sentence that we're trying to conclude is there exists x such that mortal applies to x. This is our end line that we're trying to get to. Everyone follow where we're starting and where we're going? So, what do we do first?
Drop your universal quantifiers.
Yeah, let's get this one on its own. So we're going to conclude from this that
H of x.
h of alpha, an ambiguous name now.
Oh.
We're saying alpha is, sorry, I'm going to use beta. My alphas look too much like x's. h of beta. Beta is that particular x that's human. So I know that there are some humans, therefore beta is a particular human.
Yeah.
It's a particular person, or a particular animal that satisfies the predicate is human. Okay? Now, up on this line, okay, let me continue with this. So this was what? Which rule was this?
1, 2.
Existential specification. We're not
We're
adding the quantifier, we're specifying. We're getting rid of the quantifier. We're specifying a particular one. We're talking about a beta. There could have been several x's that did this. Now we're talking about a particular one of those things. The beta one. Good? Okay. And this depends on which one?
1. I mean 2.
2. Alright. Now, we're going to do universal specification on this. And remember, we can plug in whatever we want for that x there. In this case, we're going to plug in beta now. So now I know h applying to beta implies m applies to beta. And this is universal specification. Oh, sorry. This was existential specification on 2. This is universal specification on 1. And this depends on 1 and 2. Oh, no, just 1 so far. Okay?
Wouldn't it be 1 and 3?
No, I haven't used 3 yet. I just did, all I did is universal specification on this, plugging in beta for x. I haven't used the fact that I know that there's any humans. I'm just saying if beta is a human, beta is mortal. That's what line number 1 tells me.
Right.
Okay.
I don't actually know, just from this, that there is a human.
Yeah.
Right? And then 5 is where we're going to put together. I know that there's a human, and I know that if it's a human, that's immortal. So 5 is just m beta, right? And this is tautologically implied by 3 and 4. Now we're using premises 1 and 2. And then my last line is going to be x such that mx, right? And this is existential
Generalization.
Perfect. Generalization. 1, 2. Anything weird in any part of that proof?
Is 5 supposed to be there with?
Oh yeah. What did we generalize on? We did that on 5. Anything weird? Anything you don't like? We're all good? Good, James? Alright. Oh, I need to know if you guys that aren't in high school anymore were intending on taking my classes. I won't be able to. Okay.
You're discreet, that would be the one.
Well, I just gotta get permission if you're gonna be in there. And I can get permission. There's no reason Brother Ham would have an issue with that.
I
just
could
need to
try.
do that ahead of time. So make sure you let me know if you intend to. It's perfectly fine if you do. I just want to make sure you understand that. I just gotta get the green light. Okay, next example. This is on-
Did you have a meeting with him?
Would I what?
Did the teachers have a meeting with him?
No. I think we're going to do them still.
Well, I heard the teachers had a meeting by him that they kind of, or at least sounded like I heard.
I think they did a meeting to work out the schedule type stuff. So only teachers who are heads of departments had to be there. Or maybe they did the general meeting that they usually do and I wasn't invited.
I don't think so because I know at least 2 other teachers that also weren't there.
Alright. Yeah, so I think we're still gonna have one more meeting before school starts. But
I heard they finally set an official date.
21st.
21st is officially the first day of school and then registration's before that. Alright. Let's do the next one. All mammals are animals. Let's write that one out. 1. For all x, mammal applying to x implies, animal applies to x.
Is our, I mean, just to specify here, our domain is all living things, right?
Oh yeah, in this case, our domain is all living things, sure.
You don't have to.
Yeah, a lot of the times the domain is somewhat inferred,
Right.
and
That's
you
why I
don't
was
take
just
your time to
making sure.
specify it, but yeah. Let's see. All mammals are animals. some mammals are two-legged. So how are you going to say that one?
There exists
There exists.
mammal X and TX.
Perfect. There exists something that's both a mammal and it's two-legged. And I'm guessing we're trying to prove that there's two-legged animals. Yeah, therefore some animals are two-legged, right? So, same thing, starting with this, we're going to do what?
Gonna existentially specify it.
Existential specification. So if there is some x that this is true for, then let's call that beta. So I know m beta and t beta. Now what?
Well, then you universally specify number one.
Universal specification on 1 using beta. So I also know m beta implies a beta. Now what?
Well, now you just use your tautological implication.
Right, I know m beta is true, and I know m beta implies a beta. Therefore, I know a beta and t beta.
Right?
Right?
Uh-huh.
Anyone confused by that? And then finally,
That's
existential generalization. There exists x such that ax and tx.
it. Will you ever end up here upon beta? I guess no.
No, because when it's all said and done, you better have a sentence.
No.
This is something that we can
Right.
call true or false.
Right.
This isn't.
Why not?
Because
A beta and T beta, true or false?
True.
All right. Let's do the next one.
just the
It's a
free
little more
variable,
interesting.
you're saying the free variable is gonna, that knocks it out of making sense.
Yeah, we don't have free variables in interpretation, so you have to apply an interpretation to that. And you have to treat those basically as variables. And so pick something from the domain to plug in for that.
But if beta was a constant, it would be a sentence.
If beta was a constant. But it's not something that we know. It's not like the number 2. It's still a variable in the sense that we don't know what exactly it is. We just know it's something that satisfies that condition. Okay. Next one. All Aristotle's followers, like all of Aquinas' followers. How are you going to say that one?
For all x, such that a
AX
of x
implies q of x, I guess. I don't know.
No.
why is
No.
it implies how come
Don't you
it's
need
not
of
and?
A and X and of like,
A what?
don't you need like 2 quantifiers?
Yeah, exactly. For all y.
Yeah, that's what I thought.
That like a what?
We're dealing with another person.
What should we do for Aquinas since we already used A? We'll do B for Aquinas. For all x, x being an Aristotle follower, implies that for all y, where y is an Aquinas follower,
Then
x likes y.
Did you come?
Oh yeah.
Me? I just thought that was
you're getting
kind of
it
obvious.
way faster than me.
Well, there's 2 different things, so you kind of need 2 quantifiers. Don't
Does that sound make sense to everyone?
you?
Yeah.
That makes sense as interpretation? Okay. So that's the first premise. Number 2, what do we have? We have none of Aristotle's followers like idealists.
So for all x, not ix.
No, we still need to have an Aristotle follower first.
Yeah, but
Being an Aristotle follower implies
not ix.
no.
No.
Let's think about what this says for a second. Not ix means for everyone. If you're Aristotle's follower, you don't like yourself, or you're not an idealist. Is
Right.
actually what that's saying.
So you need a of y. Like that.
You need for all y. Being an idealist applying to y implies not like x, y.
Right. Right.
Right? That makes sense to everyone?
Yeah, I can't see. So. I think Leah's gonna come.
You told her to get over here?
Huh?
You told her to get over here?
She,
Maybe she forgot it on my
No.
list.
Well, spammer, text her 10 times. Okay. So let's see, was that our only two premises? Do we have another one?
No, there's
Oh,
There's another one.
moreover, Aristotle does have followers.
So there exists X such that AX. That's an important piece of information.
Yeah, you couldn't do anything without it.
Huh?
Yeah, keep going.
What did you say?
You couldn't do anything without knowing.
That Aristotle has a follower?
Yeah.
That's followers.
Or idealists.
Not sure what you're saying. Alright, we'll continue. Alright. Therefore, none of Aquinas' followers are idealists.
Ooh.
Okay.
Right?
Mm-hmm.
So maybe
That's
you
what we're
write
trying
the
to
statement really quick that we're trying to get to. Ultimately, we're trying to prove that for all y, being an Aquinas' follower applying to y implies that not idealist applies to y. Right?
Yeah.
So this is a statement that we're ultimately after. Okay. So let's just make that real quick. Obviously, we know what to do with this.
Mm-hmm.
Remove the
Quantifier.
Yeah, so
Yeah.
A applies to beta, universal or existential specification. Then we'll write out all these lines. I'm gonna have to get rid of this to do it. Rewriting this and this using universal specification, we're gonna get A applying to beta implies that for all y, beta or B applying to y implies like applies to beta and y.
Can't you?
Why don't you get rid of y?
Yeah.
Because it's followers, it's multiple. It's
Hold
not
on, I
one
just took
follower
this.
line or
And all I did to this was universal specification.
Yeah.
Alright, so why don't you?
I got rid of this quantifier, replacing all my x's with beta.
Why do you?
But why don't you get rid of the other quantifier? Aren't you universally specifying
Because
that too?
I don't have that applying to a formula. This is my formula right now. There's no existential quantifier applying to all this anymore.
I gotcha.
And you can only do that when it's applying to the entire formula.
Yeah, it's gotta be existential quantifier formula.
Since that's part of the formula, you can't take it out.
Right, I can't just do it to everything all the way through. No, that would give very weird behavior. Anyways, and doing it to number 2 gives us same kind of thing. Alpha, or A applying to beta implies that for all y, I applying to y implies not like between beta and y. Okay with that?
Yeah.
Okay, and then obviously I can conclude both these sentences because I know alpha beta, or
Oh.
I know a beta. Since I know a beta, I know this statement and this statement,
And then
Yeah.
and then I could universally specify both those. So I'm going to skip straight to this, make sure that this isn't making too much of a leap for you. I know that by implies L beta y, and I know that IY implies not L beta y. Everyone follow those two
So
leaps?
now that
Yeah.
X is beta,
So now,
And
using
you also-
these two together, right? What do they call it? Hypothetical syllogism. Ugh. Because this is the same thing as like by implies not IY.
Right.
Yeah.
Contrapositive of this,
Do you,
just make sure that this
you,
is good for you.
you also know
EY implies not IY.
VY and IY, right?
Yeah, that makes sense.
Not choosing these two.
So
Everyone
it's
see
not
that?
Qualification of 7 and
Contrapositive on this, hook it onto that, you get that.
Do you also know VY and IY?
I know BY implies IY. I know BY implies this, I know IY implies this.
But you don't know.
Now, just because you know A implies B does not mean you know A. If Donnie's a purple dragon, then the sun's on fire. The sun's on fire, it doesn't make me a purple dragon.
I get that. I was just wondering because it was part of an implication. If it made it true. Because
No, just the implication
You do know
is true.
A B. You do. I mean, you do know A beta.
Yeah, I know A beta. But, so for example, this whole thing, we could prove it to be true, and it could be the case that Aquinas doesn't have any followers.
Right.
All we're proving is that for every follower he has, they're for sure not an idealist. When it's all said and done, that can be known.
Right.
Okay, and then finally our last line here is to do what?
Universal generalization.
Perfect. So then we can conclude for all y, by implies not iy.
Why didn't you change y to a?
You could have. As a general rule, we use the same variable that we were already using for it, unless we have to do otherwise.
And the universal one.
Well, I'm just saying.
For our universal specification
And
generalization.
not for existential ones?
Not for existential ones. For existentials,
Oh, I
we
see.
typically go to Greek letters to make sure we understand that
This is a specific.
this isn't a variable that you can, this isn't a free variable, and at the same time, this also isn't a constant.
Well, it is one of them, isn't it? Oh, it's a
No.
it's a variable.
It's a particular thing. Sure, you can think about it as it's a variable, but it's a variable that needs a condition that this line isn't capturing.
So is it a constant?
No, it's a variable in the sense of variables versus constants in math, but it's not a free variable in the sense that there's some information about beta that this line's not capturing. Beta happened to be the thing that met this condition.
Right. But it is a variable, it's just
It's a variable, but you can't treat it the same way you treat this.
right.
AX. If I have something like this, I can do universal generalization on this. I can't take alpha beta and then conclude therefore for all x alpha beta. Right? I can't go from small example real quick. Let's say I know that there exists x such that being an odd number applies to x.
Okay.
So then I could say, okay, so then being an odd number applies to alpha.
Okay.
I couldn't then say, okay, then for all x, odd applies to x.
Right.
I can't universally generalize on my ambiguous names.
Yeah.
So in that sense, it's acting different than a free variable. So it's not a free variable.
I'm just wondering what the term is.
We call it an ambiguous name in this context.
But we
It's
treat
naming a particular thing, but we don't know what it's naming.
But we treat it as a constant.
But we treat it, well, no, we still can't, kinda. It's not a constant in that we're not talking, so think about when we went back to saying, there's a big difference between me saying there exists some number that, such that that number is odd, and saying that 3 is odd.
Okay.
The number that we're talking about is still a variable in the sense that I don't know exactly what number I'm talking about. Whatever that number is, all I know is it's odd. Whereas 3 is a particular number. So when we have this alpha here, this alpha, it's not a constant in that it's not a particular number, it's not 3. We don't know what number it is.
But
It's naming some number,
it's
but we don't know what number it's naming.
yeah, but it is naming a number. A specific number. You don't know what it is, but it's
A number with a particular property. Possibly there's one and only one number, and so maybe it's naming a very specific number. Like in the case when we said this is an even prime. But in this case, this isn't a particular number, alpha.
Right.
It's just some number that happens to meet the
But-
condition.
Right, but you
I
treat
thought
it
that's what
like
x is up.
right?
Is it x some number that happens to meet the condition? There exists a number that happens to be odd.
X is... Okay. Yes, in the sense of, we're talking about math now, this is a variable. In the sense of how we treat variables in our derivations, this is something different. And we can't do with it what we did just right here with y. Since we knew beta y implied not I
Well,
y,
of course you can't do
we
that.
could do, but why can't you do that?
Because you're.
That's what we're capturing with the ambiguous name.
Okay.
So it's still not a particular thing,
But we treat it like it is, don't we?
Well, no, because we treat constants different than we treat this thing. We don't treat it the same as a constant. We don't treat it the same as a variable. We have a special way for treating this thing.
Why did we introduce a definition for it earlier on?
An ambiguous name.
Yeah.
We're not. Does this not use it?
It does use it. But like when we did term and constant, we talked about using them before using them.
An ambiguous name is just the placeholder for when you do existential specification. That's all it is. We're calling that particular thing so that we can start using our logic formulas like we're used to using it,
Right.
an ambiguous name.
Right.
So it's like holding the place that, hey, an existential quantifier applied to this thing. Don't lose track of that information. But we're still going to do logic with it and treat it how we would a constant. But it's not really a constant.
Right.
Because when it's all said and done, we got to get back out of that state that we jumped into. How are you doing, Leah? You caught up now? Well, keep staring, you'll get there. All right. So that was the last example. Were there any questions on this example? Maybe we'll walk Leah through it real quick so that she can see everything that's happening and she'll probably catch up. So you remember the existence quantifier and the universal quantifier. So you'll remember from 4.1, we were doing proofs that just had universal quantifiers in it. 4.3, we're introducing now existential quantifiers, proofs with those in it. Okay? And so, here we're just doing the proof for this one right here. So let's go over it one more time really quick, show you what the premises are, and then how the proof follows. Okay. So all Aristotle's followers like all of Aquinas' followers. That's this one. For every x, x being Aristotle's follower implies that for every y, where y is, we used b for Aquinas' followers because a was taken. So for all y, where being Aquinas' follower applies to y, then it's the case that like applies to x and y. You follow that? Similar thing down here. None of Aristotle's followers like any idealists. So for all x being Aristotle's follower implies that for all y being an idealist implies the like relationship does not apply to x and y. And then the last one here is where we're using the existential quantifier. Moreover, Aristotle does not have, or does have followers. So what does that mean? That there exists some person such that they're a follower of Aristotle. Now, this step to this step is what we call existential specification. So there's two ways that this works. We have existential specification, which is going from formulas like this to formulas like this, and existential generalization, which is going from formulas like this to formulas like this. So I know that if there exists x such that a of x is true, then I can call one of those particular x's beta. Right? If it's true for some x's, it's true for a particular x, we're going to call it beta. And then we can use a beta the way that we're used to using it in logic. So then I know that there's some beta such that beta is one of Aristotle's followers. Well, beta being one of Aristotle's followers implies for all y, if y is a follower of Aquinas, beta likes y. And beta being Aristotle's follower implies that for all y, y being an idealist implies beta does not like y. Good there. And then we skipped a step and went straight to this. The next step here would be, since I know A applies to beta, and I know A applies to beta implies this, and A applies to beta implies this, then I know just those without the implies, right? Mm-hmm. And then we just do universal specification the way that we're used to it. So universal specification here and here gives me this and this. Good? Finally, going from here to here, we take the converse of this, contrapositive, thank you. Yeah, I I said it. Take the contrapositive of this, which is like by implies not iy, right? And then plug that on here. So by implies not iy.
Right.
Make sense? And then finally, universal generalization, and this is what we're trying to prove. We were trying to prove, therefore, none of Aquinas' followers are idealists, or for all y, being Aquinas' follower implies you're not an idealist. Good?
Ken, really quick, do you remember the definition for an atomic formula?
For an atomic formula. An atomic formula was a predicate with the correct number of associated terms. Something to that effect. Okay, so there's that example. Any more questions? Ready to move on?
What's an idealist?
An idealist. How's the simplest way to say this? Because it captures a whole school of thought thinking that A, the ideal can be achieved, and also that the ideal exists. So the first idealists and realists are typically brought up is Plato versus Aristotle. Plato was an idealist, thinking that you probably read a little bit of his stuff, ideal forms actually exist and that those things can be achieved. Aristotle was a realist in that, no, what's real is right here around us.
Right.
This isn't a shadow of some perfect chair, the ideal chair. And it's not that the ideal chair is real and that this is a shadow of it. This is what's real. Idealist versus realist. That's what's rooted in, but honestly, how those terms are used more and more become disconnected with the actual words that are used for them, and more just what they get applied to. It's like, what's a political term? Being pro-choice versus pro-life. If you're pro-choice, what does that really mean? Does that really mean you're pro-choice? No, that means you're for someone should be able to have an abortion.
Right.
That doesn't mean every choice out there, you're for that choice, and so the word can be very misleading. Same with pro-life. Does that mean you don't kill bacteria? No, that's not what it means. So they're words that the people who have associated those words with themselves have warped the meanings of them, and so it's not just here's what it is in one sentence. Anyways, let's continue. Okay, so that was all 4.3. Nice and simple.
Well, that's it.
Yep, that's it. If you remember, 4.1 was pretty simple like that too. It was the problems that took us forever. So let's move on to 4.2, or 4.4. 4.4 is just giving us some of our restrictions, some more restrictions on when we can, oh no it's not. Oh, 4.4, so we already covered 4.4 by accident. So we'll recover the idea. 4.4 was the idea that not for all x, some statement about x was logically equivalent with there exists x such that not s of x.
We've already
Didn't we have to do that in reverse though? Like, if we had to use that in the textbook already, why are we really using it?
I don't think we have
Scroll
these.
down to 4.4.
That's good.
When you're all big.
Yeah, it takes forever.
Oh,
4.4. Interchange of Quantifiers. Okay, so here's the idea that 4.4 is going to capture, one of the major ideas that's going to capture. And then the second major idea that's going to capture is the idea that if A is tautologically equivalent to B, you can swap them out. So in other words, I know 3 plus 5 is equivalent to 8, so I can swap those out for each other type thinking.
Right.
So those are the two big pieces of it. So that's what Q1 and Q2 are going to capture, basically this idea. And then rule tautological equivalence is going to be the idea that you can swap out equivalent pieces of formulas for equivalent pieces of formulas and you're still good. And then we'll do an example. So let's go over Q1. So if x is any variable, and if formula S results from formula R by replacing at least one occurrence of the universal quantifier for all x by, let me make sure. Oh, that's why they're saying this. Okay, all they're saying at the start, sorry. So if x is any variable is basically just saying, okay, so we're going to have two formulas, S and R. The variable they're in terms of is x. Okay, sorry, got confused for a second. Okay, so let's restart. If x is any variable, and if formula S results from formula R by replacing at least one occurrence of the universal quantifier for all x by not there exists x such that not, then S is derivable from R and conversely. So what is that saying? That's saying if I know that for all x, some formula about x, some statement about x, then that is logically equivalent with not there exists x such that not S applying to x.
But I thought we just established that. Oh, right. If not for all. Yeah.
So it's almost the exact same idea, slightly different. Because we have two negations over here instead of a negation over here and over there.
What?
Here's what I had right up here before. We had before that not for all x,
Oh, right.
S of x, is logically equivalent to there exists x such that not S of x, such that not S of x.
Right.
So we had a not on either side. They just put both the nots on the same side. So do we all understand what Q1's saying?
Oh, yeah,
Let's go over it one more time looking at this. So if x is any variable, and if formula S, let's see, over here this thing's going to be formula S. Sorry, we're duplicating S's here. Formula S results from formula R. So here's R, here's S. So if formula S results from formula R by replacing at least one occurrence of the universal quantifier with, or by, not that, not again on whatever you're applying this to, then S is derivable from R. So I can derive S from R, and then conversely, I can do the reverse of the process to derive R from S. Make sense?
Mm-hmm.
Okay. Q2, very similar thing. It's saying if x is any variable and if formula S results from formula R by replacing at least one occurrence of. So if we replace there exists x, so now we're saying that this is logically equivalent to
Didn't it just say
not
conversely?
for all x. Yeah, but it wasn't the same thing. Not S of x. So let's try the one that we had before. The one we had before was we could take the universal quantifier applying to some statement about x, and this was logically equivalent to not so here's Q1, here's Q2. But it was all captured from this exact idea. Here's how you distribute knots on quantifiers. We good with those?
Mm-hmm.
Anything weird there? You got it? You get tests on this a lot in discrete math, by the way. It's
Sure.
Good?
better be ready. Yeah. You'll see. Okay. And then finally, tautological equivalence. If a formula P occurs as part of a formula R, so R is the big formula and it's got some P's in there. Let's see, if formula P occurs as part of formula R, and if Q is tautologically equivalent to P, and if formula S results from replacing at least one occurrence of P in R with Q, then S is derivable from R, and conversely. So let's make sense of that real quick. So we've got R, there's going to be some big formula here, and we've got S is going to be some big formula here, and at R, whatever this formula is, P's show up in it. Some number of times, at least once. Okay? Q is tautologically equivalent to P. So we're saying over here in S, we replace at least one occurrence of P with Q. So now we've got something like this. We've got Q, P, Q over here with the middle parts filled in the same way. Then we're saying this is you can derive S from R and R from S. Does everyone understand what I'm saying there?
Yes.
Do we need to get something more concrete?
1 second, I just need to think about it.
Here, I'll write a very concrete example, and we'll just see it in action. So, let's say that we have A implies B and C. And we're going to call this whole thing right here formula R. Okay. And we're going to call A implies B formula P. Right?
Is it a sentence or a formula?
Formula. A sentence is a special type of formula. Sentence is a formula that we can determine if it's true or false.
So
Now this is a perfectly valid formula, right? It's a very simple formula. We dealt with formulas like this forever ago, right?
Yeah.
So here's one. And we know that A implies B is the same thing as not A or B.
And you call that Q.
And C. So we call this part Q, and we're calling this whole thing over here S.
Why are we calling them different things? They're the same thing.
P is tautologically equivalent to Q, but they have different forms. So let's read what this is saying one more time. If a formula P occurs as part of a formula, sorry, I lost my place. As part of a formula R, if a formula Q is tautologically equivalent to
P.
P, here we are, and if formula S results from replacing at least one occurrence of P with Q in R, so take R, replace P with Q, that's how we get S, then we know that R and S are tautologically equivalent. We can derive S from R, and we can also derive R from S.
Right.
We can go back and forth between those. It's a pretty simple thing that we've already been doing, but there's our rule for it. We good with that? Anything weird? Anything confusing? We can't hear you when you all talk at once.
So,
I'll be there.
Alright, so let's do an example then. Okay. So, if there is a federal court which will sustain the decision, then every member of the bar is wrong. Alright, let's write that.
Okay, if F.
If F, do you want me to write if?
No, F implies.
B.
Wait 1 second.
Okay, let me give you a hint.
We're all.
We're going to have to use quantifiers.
Yeah.
so
Okay, for all X, if it's a federal court.
no,
No,
not for
there-
all. There exists an X.
Yeah, there is.
X, F.
FX
FX.
implies SX.
There exists a member.
Like that?
Wait a minute,
No,
no.
we should end parentheses after
Ah.
this.
Good. Like that?
Yeah.
Uh-oh.
Wait a minute.
If there's a federal court.
I don't know if I'll wait that long,
will
but
sustain the decisions.
if there exists a federal court
Bar.
which will sustain the decision,
So is it and
there we go.
SX?
And SX.
All
Okay,
right.
that
And
implies.
X is the domain of decisions.
Sure. No, it's people.
And what's the
Then
decision?
what's federal court?
There exists someone who is on the federal court who will sustain the decision.
Oh, I thought FX was covered.
Okay.
And
That
Okay.
every member of the bar is wrong. So
So,
for
for
all
for all
y.
Why?
not
Just
BY
gonna write X, we can just
or not something Y,
well,
Yeah.
not WY.
BY
applies
implies
for all X.
not R.
Let's see where
B
we
of X,
B of X implies
not R.
not
Right.
W. Not wrong, right?
Not
Then every
wrong.
member of the bar is wrong. Now then it implies wrong.
Oh.
Well, not right.
Is wrong implies not right though. So I mean, either way. it
I
doesn't
see what
matter.
you're doing.
Yeah.
Which one do you do? Do you is wrong or is not right?
If there exists X such that Fx and Sx, then for all X, Bx implies Wx. Good?
Mm-hmm.
Huh? Okay. Makes sense to me. Alright, next one. Next one is, however, some members of the bar are not wrong.
So there exists X such that
B of X
Why are we
implies
doing
not
fees?
X.
Member.
should be M, yeah. MX implies not WX.
Isn't it and not Wx?
Oh,
And
and not WX.
there exists someone who's a member of the bar and they're not wrong.
Right, right.
And what are we concluding? Therefore, no federal court will sustain the decision, or we're trying to conclude that for all X, F of X implies not sustained. Right?
Okay.
We're trying to get this. For all X, being a federal court applying to X implies not sustained the decision.
Scraps here.
Wait a minute. Whoa. Okay, that's a little weird.
It is?
Yeah. Well, it just seems like the opposite. It seems different from number one. A little bit.
Alright,
Contradiction, guys.
so
Yeah.
let's do this.
Well, you dropped the quantifiers.
We could, but why make it a mess? Let's just really quick write down the contrapositive of 1. What do we get?
You get not AX.
We get there exists X such that we need to do the not of this. I'm just going to write it. Hopefully you guys can now keep up with this.
And not WX. Right. Man, you're skipping steps here.
Right.
Well, we do this so many times.
Contrapositive, guys. Top line.
Yeah. it's
Contrapositive of the top line.
a lot of things. If we did that on homework, you'd get pretty upset with us.
Huh?
So if we did that on homework, pretty upset.
Yeah, every time I see this on homework that gets turned into me, I'm throwing it right back at you. By the way, you're way behind. You're the only one. Everyone else is caught up.
Yeah, we're
So.
What do you mean?
Missing your homework. All right. Anyways, so here's the contrapositive of 1. The antecedent of 3 is 2.
Right.
Therefore,
For all X, F of X.
Wow, that's pretty
implies
crazy.
Not X.
so
Didn't even have to make a mess of it.
yeah, you didn't need to go crazy getting rid of all your quantifiers and putting them
Oh,
back.
whoa.
You could if you wanted to. But there we go.
Then did you even need a second line?
Yeah.
That's the second one's pretty
3 is the contrapositive of 1. And 4 is combining 2 and 3. If I know that A implies B, and I know A, then I know B. So I had to use both these lines. Good?
Mm-hmm.
You sure?
Yes,
You promise?
I promise. Pinky promise.
Oh boy.
Come on,
Alright. So there's that. And that's the end of that section. Pretty simple, right? Once again, I strongly recommend reading through the sections because the author is going to try and establish intuition for you about how all these work. Okay. Now, 4.5, general inference, but basically what we're going over here is restrictions. Our different restrictions on how we can use our generalization rules and our specification rules. So, in practice, your intuition stops you from breaking a lot of these things naturally if you keep track of what it is that you're talking about, right? You intuitively know that if I find a number that's even in prime, I can't conclude that every number is even in prime, and you naturally don't try doing stuff like adding proofs, but these restrictions are just making sure, hey, don't try doing crazy stuff like that, because we're coming up with rules to make sure that you cheat. Okay, so let's look at some of these restrictions. Restriction on universal specification. Do not substitute a term containing a variable which becomes bound. Okay, so what are we saying there? So here I say that I know for all x, think about this in terms of numbers, for any number, I can find another number such that the number I find is greater than the number. For every x there exists a y such that y is greater than x.
Yes.
That's true. For any number you pick, I can always find a number bigger, right? So we might be tempted then to do, okay, universal specification replacing x with y. All right, so now I said, okay, now there exists y such that y is less than y. Because I did universal specification on x plugging in y. Y was already a bound variable in my formula, and you just try doing universal specification with y. Doesn't work. Does everyone understand how this is true but this is false? There isn't any number that's less than itself.
Right. But
Except for that one.
Zero.
0 is less than 0.
Let's not talk about
Well, that's small. Okay. So everyone understands this restriction?
wait just a second. Isn't the point is saying don't replace variable for a bound variable?
I can't do universal specification on a variable, giving it a name that would then make it bounded.
That would then make it bounded.
Yeah. So
Oh.
notice that
Right.
I could plug in y because there exists y as a bound variable.
So you basically, okay.
Right? I could have plugged in basically I could have plugged in anything for x but y. When you look at this, the only thing, and you intuitively understand, the only thing I can't plug in for x is y,
Right.
and it makes perfect sense. Right? Okay. And then restrictions on existential generalization. Do not replace ambiguous names with bound or free variables. And we'll see an instance of where both these go wrong. So let's look at a quick proof right here. So I'm saying that there exists an x such that for every y, x plus y just gives you y. What's the x we're talking about?
0.
0. I'm saying there exists a number, namely 0, such that 0 plus any number is just that number. There exists some number, x, namely 0, such that for any y, x plus y equals y. Everyone understands how 1's true? Okay. So now, going from here to here, we do existential specification. So we say, okay, then there exists some alpha, such that for all y, alpha plus y equals y. And once again, we know that that alpha is 0. Now, here's where I cheat. When I try doing existential generalization on a bounded variable. Because remember, when I replace alpha, I can replace it with any variable. Well, don't replace it with a variable that's already bounded. In this case, if I go now and I replace it with y, which is already a bounded variable, then I get the statement, there exists a y such that for all y, y plus y equals y.
0. Got him.
There exists a y 0 such that for all y,
Okay.
it's broken. It doesn't work anymore. So when you're doing existential generalization,
A y, 0, such that for
For all numbers.
all
For any number I pick.
there exists a number such that for any number, double that number, and you get that number.
Right.
Now we don't even know how to do that, right? It's a broken statement. You come across this in your book, you're saying, what's that saying?
Right.
Okay. So we do not replace ambiguous names with bounded variables, and we don't replace them with free variables. So let's see that over here. O in this case is going to be odd. So I take there exists x such that x is not odd. That's true. There exists some not odd number. And now I have odd applies to x here in this premise. Notice that this premise is a free variable. So this would be like something that we do stuff like this all the time in like a conditional proof. We introduce a condition, tells it implies a conclusion, but there's nothing wrong right here. We can introduce a premise whenever we want, right? Alright, so I have there exists x, such that not being odd applies to x, and I have odd applies to x. Okay? So from here, I can get not odd applies to alpha. Sorry, that's an alpha. Let me just replace my alphas with betas. So it's more readable. Okay, so I have not odd applies to beta. So I have OX and not O applies to beta. So far everything's all good. It's when we go from here to here that we cheat. I can't replace. I said free variables. Flagged.
Oh, okay.
Sorry. Remember what a flagged variable was? It's a variable that in its premise was free. So notice that 4 depends on premise 2, which has a free variable x in it. So x is a flagged variable.
So
you remember talking about
can't
flagged
generalize
variables?
off of it.
Yeah, you can't existentially generalize flagged variables.
Right.
That's what we're saying here. So then, when we go from here to here, when we try to existentially generalize, we get a broken statement. There exists x such that x is odd and x is not odd. No, there is no number that's both odd and not odd.
Right.
So going from here to here is where we cheated. Good? Anything weird? Like I said, most of these restrictions you naturally don't come across because you don't try to do weird things. Like I would never have the x here and then use an x here to begin with.
Why would you?
And then if I did have an x here, when I did an existential generalization on beta, I wouldn't put it back to x. I'd put it to something else typically. I don't know. You naturally just avoid these situations. Like we never thought about what we could and couldn't do here. We just kept working with it. And you'll find out that it's very rare that you actually come across these restrictions. Every now and again you do, but it usually just makes sense to you why you can't do it. Anyways, so there's some restrictions. Now let's just do kind of examples where we're not even going to notice these restrictions because we're just going to do them the way that they make sense. So we're going to now go through all these examples. Good?
Yeah.
I'm going to need some space over here to write. We got plenty of time. All right. Let's see the first one. All dogs are animals, therefore all heads of dogs are heads of animals. All right. So capturing how we get that end sentence is going to be a bit of a pain.
How are
So we know our premise. That one's nice and easy. Our premise here is
for all x, if x is d,
X.
D applying to x implies
A applies to.
A applies to x. So we use that, and what do we conclude? We just conclude, therefore, all heads of dogs are heads of animals.
how do you conclude that?
Yeah, how do we even write that sentence? Forget concluding it, let's just write that sentence. Anyone want to give this a try?
Sure.
Okay, see if you can write the therefore part.
You'd say.
Equal. Oh, it's 2 arrows. If and only if.
No, that's definitely an implication.
It's an implication, so you'd say.
If it's ahead of a dog, it's ahead of an animal.
For all x, hx
X being ahead.
and
Alright.
dx.
What
X
is-
being ahead and X being a dog.
That doesn't make sense.
You
So
could try
our
to-
x is ahead, baby.
You have to add another
You
unit.
need
For all
another
y,
variable.
and then like, for all x, if x is ahead, and then if y is a dog, and then.
Maybe maybe for all x.
No,
there's
no,
this
I'll give
one.
you-
You need an
Let's
X
think
and Y,
about this
and
for
then you
all
have-
Y as for all heads. Okay, so for all heads, we'll
There's
start with
just an
that.
animal head and a dog head.
You'd say
For all heads,
If
You
it's
also
a
need
dog
for
head,
all
it's an animal head.
dogs, don't you?
no,
D of y implies A of y.
maybe I'll give you the next part. Sorry, I'm cleaning up a little. So for all Y, if there exists X, where
Where y dx
Oh, yeah. D y x
or
and
dyx, either way,
and
you're right.
a y
Where
implies a y.
dx, D can only take one term. We want it to be a one-place predicate.
And hy, then
X. Alright. So for all heads, if there exists something that's a dog and Y is the head of it,
right.
that implies there exists something where that something is an animal and Y is the head of that animal.
Yeah.
For all heads, if there exists something that's a dog and Y is the head of that dog, or Y is the head of it, then there exists something that's an animal and Y is the head of it.
Okay.
Everyone understanding the sentence?
So you're supposed
For
to-
all heads Y, there existing something that's a dog and Y being the head of it implies that there exists something that's an animal and Y is the head of it.
There's another unspoken premise then that we have to
No.
state.
There's no
You
unspoken
can't
premise.
just introduce the H out of nowhere.
And the Y.
Sure I can. That goes way, way back. We can introduce a premise at any point
That's
we
like-
want,
that's what I'm
whatever
saying.
crazy
There's-
premise you want.
There's an unspoken premise that we need to state. That was
Well, yeah, it's a conditional proof. We need to introduce this as a conditional premise, show this, but when it's all said and done, we don't depend on that premise. Proof, it's gone. So, we introduce this, we say,
For all heads.
we just introduce this part, sorry, the antecedent of the implication inside the quantifier. So here's what I'm saying, and maybe it will just already make sense, and I'm wasting my breath saying it to you guys, but.
And the y is just a free variable.
Yeah, right now it's just a free variable. So this is just a conditional premise. Maybe we'll write out our stuff for this one since.
So you're saying on line 2 you
Next
just did universal, general, or specification.
I haven't done anything yet, I just introduced a premise as a conditional premise. It happens to have a free variable in it, so what? Happens to have HYX in it, so what?
Alright.
I can introduce anything I want as a premise at any point, as long as when it's all said and done, my conclusion only depends on one.
You know your premises have to be consistent.
My premises have to be, so we talked about premises being consistent towards, well, that's not necessarily true. Yeah, my premises do have to be consistent. That is the case. But we already know that there is an interpretation that could make both these things true.
Yeah.
Yeah.
You don't have to prove they're consistent, but they have to be.
No, we proving that they're consistent, we usually do that with a set of axioms. Because when it's all said and done, whatever I have is only going to depend on one. It's not going to depend on this. I don't care really if this is consistent with this, because when it's all said and done, that's not going to be a premise. I'm going to get a conclusion that only depends on this.
Okay.
Anyways, so then we got that. So, what's number 3?
Specify it.
Yeah. Not universal, existential specification. Therefore, D applying to alpha and HY alpha.
Right.
And that was not universal existential specification on 2. And this now still only depends on 2.
And then you can imply AX and HYX, right?
Yeah, if we want to write out the proof all the way, we need to really quick on this do universal specification. So D alpha implies A applies to alpha. That's universal specification on 1. This only depends on 1. Now we combine those and we get A applies to alpha and HY alpha. And that is tautologically implied by 3 and 4. And we're using premises 1 and 2.
So now we can't generalize this, is what their whole point is.
No, we can. Now I can do existential generalization on this.
Well, you can't touch that Y.
No, I have to leave the Y alone. So I couldn't, so far, I couldn't plug in, well, I couldn't existentially generalize on Y because Y is still a flag variable here.
Right, that's what.
Yeah, but I can with my alphas.
But you can once you remove it from the premise.
No, I can never do it on, once it's not a flag variable anymore, then yes, I can do whatever, I can treat it
So when
just
it's
like everything else.
back into the implication and not a conditional premise, then you can do that.
Correct. So now there exists some X such that A applies to X and H, Y, X, right? And this is existential generalization on 5. And this depends on premises 1 and 2. And now we finish our conditional proof. So I showed that if there exists X such that dx and hyx, that implies there exists X such that ax and hyx. This is my conditional proof, and it was from 2 to 6, and now we only depend on premise 1, right? And then we universally generalize on that, and we're done. Right? My last line would be, and for all y, you could do square bracket, there exists x, dx and hyx implies there exists x, ax and hyx. Good?
A little more confusing than usual, but that just makes sense.
Yeah, that was a cool one because the premises were really simple and what we were trying to prove is very convoluted. So we have to look at what we were trying to prove, figure out what our conditional premise was going to be, and work from there. So that was a cool one. Even though when you look at it, you think, oh, well, that's got to be just one liner, right?
Right.
Nope. Okay, let's do the next one. Occam's. As in Occam's razor.
I don't know what that is.
Have I heard of Occam's razor? Alright. None of Occam's followers like any realists. So what does that mean? So for all x, being Occam's follower applying to x, maybe you guys can figure this out. It's going to be just like the one we did. What does that imply?
There does not exist. There
For
does
all
not
y,
exist.
ry implies not lxy.
Perfect. Being a realist applying to y implies not like applies to x and y. Right?
So all of Occam followers are idealists.
No, not necessarily. They just don't like realists. Maybe they hate themselves.
Cute.
Okay. Continuing. Lots where we were. All right, here. Any of Occam's followers like at least one of Hobbes' followers. All right. How do we read that? Hobbes. Well, in short, he's an Enlightenment thinker philosopher.
I guess Occam was too, huh?
Yeah.
I'd say how we have already used awkward razor then.
I've never heard of Occam. It's not a
I
razor.
thought it was a brand. I was like, you've used a brand 50 years old.
Ah.
Just messed up.
That's
70
great.
years old.
Okay. Continuing.
Shoot.
Any of Occam's followers like at least one of Hobbes' followers.
For all
At
x,
least one.
for all x, ox implies
There exists y
There's just a Y.
such that hy
H.
and lxy.
Perfect. Everyone get that? For every person, if they're a follower of Occam, then there exists someone who's a follower of Hobbes who you like.
this was just like Aristotle.
Yeah, it was very similar to that other one.
Mm-hmm.
Slightly different, but very similar. Okay? And then we should have one more premise about Occam has followers. Occam does have followers, yeah. So there exists x such that Ox, like that, right? And what are we trying to prove? We're trying to prove, therefore, some of Hobbes' followers are not realists.
There exists.
So we're trying to get to, there exists x. Down on me.
Yeah.
So we're trying to get to, there exists x where, what?
There exists x such that h of x and not r of x. Or what are we doing to L of x?
Perfect. So, where is it therefore? Therefore, some of Hobbes' followers are not realists. Therefore, there's someone who's a Hobbes follower and not a realist.
I just didn't know if we were using r. Yeah, we were on there. So.
Oh, yeah. Okay, so let's do this. First thing we're going to do is what?
Specify.
Specify existentially or
Yeah.
universally?
Exists.
Existentially.
Alright, so you're basically saying O of
Beta.
beta. Alright, now what?
Now you.
University stuff.
Yeah.
Yeah, so now we can do O beta implies that for all y, ry implies not L, x, y, and we can also do,
Wait,
Don't you have to replace x
L
with
beta.
No,
Oh,
this
thank
is
you.
universal.
yep,
It's universal though, not existential.
universal specification. So I'm doing universal specification on this, replacing x with beta.
Can.
That's what you do when you universally specify. You get rid
I
of
thought that's what you do when you existentially specify.
both. Anytime you specify, so universal specification means we're getting rid of a universal quantifier. Existential specification means we're getting rid of an existential quantifier. So when I universally specify, I get rid of the universal quantifier. And then for every variable that was associated with the universal quantifier, in this case x, I replace it with something I'm specifying. In this case, beta. So if I replace that with a beta, I have to replace that with a beta. I have to replace all my x's with whatever.
Last time we were doing this though, it was for all x and or it was for all y. You were like, okay, I'm just gonna leave this as y because we're using beta.
You can choose.
Yeah,
whatever
so
variable.
also what you're thinking is what we'll do here in a second. So this one's also, oops, not for all y. This one's, there exists y such that hy and L
beta 1.
beta y, right? Use that for a second. So now, since I know O applies to beta, I can take the conclusion to this and the conclusion to this and just write those. So then I know that for all y, ry implies not L beta y. And from this one, I know that there exists y such that hy and L beta y, right? Now here, when I do my universal specification on that, I'm not going to want to do that because in this case I'm going to replace my y with, what should we use?
Alpha.
We want to use alpha, even though it looks a lot like x. So doing existential specification on this, I'm going to use h, and he says alpha, and L beta alpha. And now I'm going to do universal specification on this with alpha. And that gives me R. Sorry.
So what were you saying then?
Yeah, it didn't end up happening on this because this was an existential instead of universal. R alpha implies not L beta alpha, right? Contrapositive on this along with this gives me
R of X.
H alpha and not R alpha. You see that?
No. Oh yeah.
Okay. And then with this we do our existential generalization. So then we know that there exists X such that H X and not R X. And we're done.
You just cheat?
How'd I cheat?
You turned to oh no.
I could have switched that to a Y if I want, doesn't matter.
No. What I thought you did was switch a Y to an X. But I'm realizing you didn't. Because you only switched your alphas.
Yeah, only the alphas got switched.
But you didn't have to deal with any betas.
And you didn't have to deal with those pesky betas. Alright, everything look good there? Anything weird? Need me to fill any blanks?
1 second.
What was the conclusion again?
Hobbes has followers that aren't realists.
So, what would happen? No. Oh, sorry. So the part that's kind of holding me up is when you are dropping your universal and existential quantifiers on y.
From here to here,
Yeah.
okay?
So I see what you're doing, and like, it makes sense, but what would happen if you were to drop it off of the universal one first and keep the y, and then do the existential one? You so change.
Then I just can't connect them. And so then I need to go back to generalizing on this and then replace it with alpha.
So what you did is basically did the existential one first and then the universal one?
Yeah, because this needs to talk about, this one can only talk about alpha, this one can talk about anything.
Okay.
So this one's restricting what I can talk about, this one can talk about anything. Make sense?
Yeah.
Yeah? Yeah? You gonna make me wake up my baby?
I got sidetracked.
There's a lot to sidetrack yourself in here.
Well, it's hard to stay focused when it's that.
Well, I figured that this room is 13 feet.
You're so
13 6 inches.
13 feet and 6 inches? Alright, we'll measure that. In the meantime, is there anything in this proof that you like or don't like? Forget the room.
Yes, that makes total sense.
Does it make sense?
I don't know.
Alright, let's get you back to the point you can peaky promise. Do you understand our 3 premises?
No.
Alright, back to the beginning. Let's read the sentence. None of Occam's followers like any realist. So for all x, x being one of Occam's followers, implies that for all y, if y is a realist, x doesn't like y.
Okay.
Alright? Next one. Any of Occam's followers like at least one of Hobbes' followers. Another way to say that is every one of Occam's followers like at least one of Hobbes' followers. So for every person, if they're one of Occam's followers, there exists another person that's Hobbes' follower, and Occam's follower likes them.
Okay.
This one says Occam has some followers. So there exists at least one person that's Occam's follower.
Okay.
Grab one of those people, call him beta. So beta's Occam's follower.
Okay.
Well, if beta's Occam's follower, then we know that for all y, where y is a realist, beta doesn't like him.
Mm-hmm.
We also know that if beta is Occam's follower, that there exists a y who's Hobbes' follower, and beta likes him.
Mm-hmm.
Now, since we know that Occam has a follower named beta, since we know the antecedent of these two implications, we know the implications are true. If I know A implies B, and I know A, then I know B.
Okay.
So I know A implies B. Since I know A, then I know B. So in other words, I know this and this, which is what we have here and here. So I know that for all people, if they're a realist, beta doesn't like him. And I know that there exists a person who's a follower of Hobbes, and beta likes him.
Mm-hmm.
Okay? Now, looking at this one, we're doing existential specification. Since there exists someone who's a Hobbes follower and beta likes him, then I can say there's some alpha
Someone. Yes.
who's Hobbes follower and beta likes alpha. Right? Well, what does that mean? That means that if alpha is a realist, beta doesn't like them. Right?
Mm-hmm.
Well, take the contrapositive of this. That means the contrapositive of this is if beta does like them, then they're not a realist.
Yeah.
So I know that they're not a realist.
Okay.
Right?
Mm-hmm.
So this piece together with this turns this into this, and I still know that alpha is a follower of Hobbes. Therefore, there exists someone who's a follower of Hobbes and not a realist, which is what we're proving. Whew. Good? Leah, how tall is the wall?
Good question. Look at that.
All right. Whew. This next one's got a lot of info.
That is one example.
Yeah.
Hold together.
That's one example. For every x and y, if x precedes y, then y doesn't precede x. Okay. So number one,
For all.
I'm going to introduce a convention to you guys that I'm going to start using because it's driving me crazy writing so many. For all x and y, instead of for all x, parenthesis, again for all y. I'm just going to do it like that.
Okay,
Okay.
not simple.
That one extra step is really killing you.
It is. Mostly this is my gut way to write it, and I've had to like stop myself and write it different every time because that's how you write it. Okay, so for all x and y, if x precedes y, that implies not y precedes x. Right?
Okay.
For every x, y, and z, if x precedes y and y precedes z, then x precedes z. Okay, so it's transitive. So for all x, y, z, if I know x precedes y and y precedes z, I know x precedes z.
Crazy.
Insane. Good?
Mm-hmm.
For every x and y, x precedes y, then x is not equal to y. Okay? So
Are we thinking about these in terms of numbers? Or what?
we're not applying interpretation because we're doing a proof. You can just work with the formulas, but you could think about the precedes as x is greater than y if you want to think about them in terms of numbers. Anyways, for all x, y, if x precedes y, that implies x is not equal to y.
Honestly, I was thinking about a horse race.
Yeah, you can think about it that way. Think about precedes as is ahead of, and equals as they're neck and neck. Yep, that works perfectly. That's what I said, right? If x precedes y, then x is not equal to y, yeah?
It's not equal just a predicate.
Yeah. Because remember, this is a statement. No. Sorry. This isn't a term, is what I meant to say. X is not equal to y, or x is equal to y.
That's a sin.
It's not a term, so I can't be an operator, so yeah, it's predicate. what were we on? For every x, y, and z, if y is between x and z, then either x precedes y and y precedes z, or the other way. Okay. So for all x, y, and z, if between applies to x, y, z, notice I'm putting the line in the middle of them. So if y is between x and z, then that means one of two things. That means we either have
No.
x precedes y and y precedes z, or we have z precedes y and y precedes x.
Did you do that wrong? For every x. Oh, sorry. Wait. Where are you?
Right here. For every x,
Okay,
y,
yeah.
and z,
I was
if
gonna
y
do
is
that.
between x and z, then either x precedes y and y precedes z, or z precedes y and y precedes x, which is what I wrote. Next, for every x and z, if x is not equal to z, then there is a y between x and z. So 5 for all x and z, not between, sorry. If x is not equal to z, that implies that there exists a y such that between x, y, z. Right?
That doesn't work with numbers. If with integers.
Not with integers, work with real numbers. So that's a geometric property, and the geometric line is equivalent to, well, maybe I should say equivalent to, but we have to use the real numbers to capture
Right. It's continuous.
the real number line,
Right.
which is what we're using in geometry. Yeah, so that's a geometric property. So yeah, has to be at least rational numbers. I guess right now it doesn't have to be real; it can just be rational. And that's all we need. And that's that. So therefore, for every x and z, okay, so where we're trying to get is for all x and z, if x precedes z, then there exists y such that x precedes y and y precedes z. Okay. Then there exists y such that x precedes y and y precedes z. Whew. That one's a mouthful. You see what we're trying to prove and all the premises? Do they make sense? Are there any questions, or are we just ready to start going?
Oh, that makes sense.
Oh, yeah.
I
Anyone
got lost
confused?
at 4.
Number 4. Number 4. So basically, if I know that y is between x and z,
Okay.
then either x is greater than y and y is greater than z, or z is greater than y and y is greater than x.
Right, that's just right.
Okay.
Make sense? Okay, number 5 is saying if x and z aren't equal, then there exists some y between them.
Right.
Okay.
Now down here we're saying, for any two x and z, if I know that x precedes z, then I know that there's some y between them, where x precedes y and y precedes z.
Isn't it? Saying the same thing as 5?
Isn't that saying the same thing as 5? No. Nope.
For all.
This is
x
giving us a
and
particular
z.
order, this is just saying in between. Alright, anyways, let's begin. Obviously, this is a conditional proof, so we're going to start out with assuming our antecedent,
That was an obviously conditional proof.
Because it has
because we're trying to prove that this implies this.
here.
So I need to start with this and show that we end up with this, and therefore this implies this. Make sense?
Yeah.
Okay. 6, we start out with x precedes z. Okay, if I know that x precedes z, what do I know?
You know, not y.
I know that not y precedes x, right?
Mm-hmm.
And I also know, what else do I know if I know that x precedes z?
X is not equal to z.
X is not equal to z. Oops, I put a y there. I know z does not precede y, and I know that x is not equal to z. Did I say y again?
Yeah.
We only have z's and x's so far. No y's. Sorry if I keep confusing it. I know x precedes z. Therefore, I know that z does not precede x. That's from number 1. And I also know that z is not equal to x. That's from number 3. I'm not going to bother writing all these ones out because it would blow up and get really big.
Yeah.
Good so far? Okay. So, let's see. We know that x is not equal to z. What does that give us?
Gives you 5 for every y there exists a y.
It gives us
X
that
and Z.
we won't bother with the there exists, but it gives us that b x y z, right?
Why would you just ignore a quantifier?
Well, I guess I could put a beta here or something. So, since I know that x isn't equal to z, I know that there exists some beta such that beta is between x and z. I'm just going really fast, skipping steps. I think you guys can all follow this here, right?
Mm-hmm.
So, since I know that beta is between x and z, then I know what?
Then you know either y is between x and z or y is between z or x.
Then I know this one or this one.
Mhm.
Uh-huh.
Now, I'm not going to bother with the beta, I'm just going to use a y. Hopefully that won't throw you guys off. There exists some y such that y is between x and z. What does that mean? That means one of two things. That means x precedes y and y precedes z. Or z precedes y and y precedes x. I know one of these two have to be the case. Right? Did someone say y or something?
No, I said well.
Well, what?
I was looking at the premises to see.
That's just this one. Since y is between x and z,
Well, I was looking at the other premises, so I was trying to find like that.
y is between x and z, therefore, y is between x and z implies x precedes y and y precedes z, or z precedes y and y precedes x. One of these two things has to be true, right?
So now you need to prove that the other one
At
is
least.
false.
Yeah, I need to prove one's false. How do we typically show something's false?
Counter
Or
or
Proof by contradiction. So, assume by way of contradiction, which one do we know is going to be false? This one's going to be false. So, by way of contradiction, zpy and ypx. We're doing this one by way of contradiction.
It's or.
No, I'm assuming this one's true. I'm going to show that that can't be, which is going to mean this one's true. Which then we're going to be done.
Uh-huh.
So, zpy and ypx, what does that give us?
ZPX.
Zpx, I don't know why I put parentheses there. And then we have zpx, and what else do we have?
No, it's UPA.
And not zpx. If you'll look clear to the beginning,
Right there.
right here,
Yep.
there's our contradiction. Therefore, coming back out of our proof by contradiction,
XPY.
we know not z, p, y, and ypx. And if we know this or this is true, and we know that this is false, this one's true.
It's true.
So then we know x, p, y, and y, p, z.
which shows you.
And therefore we know that there exists x such that that's the case. Or there exists y such that that's the case. Right? I just kept y's instead of betas. I should have switched to betas and then switched back to y's, but who cares? So then I know that there exists y such that x, p, y, and y, p, z. Therefore I know this. Oops, this is 2 steps. Therefore I know this without the quantifiers.
and then with.
Therefore I know it with the quantifiers. Make sense? Not too bad?
Quite fun to follow.
Huh?
Quite fun to follow, actually.
All my markers are dying on me.
See, we thought it was just the academy. Turns out people don't know how to make markers.
It's not great anymore. Which one was doing the best?
Black.
I didn't try the black yet.
You did. You were playing with the black.
I was? Oh man, that was not great either.
We just got a pad to just
Well, blue is definitely not good. Which of these do you see best?
black.
The black one?
Yeah.
Okay. We'll continue with that and then I'll have new markers for next time. Okay.
He has to run to the office.
Actually, they're just in my room. We're way past restrictions.
Doesn't that end chapter 4?
All horses
Oh, we
are
got a
animals,
lot
therefore
of
all heads of horses. You have to do that.
What's
Yeah.
that? 3 seconds?
Do that. And we just did example 10. Here's example 10.
20 lines of
Okay.
data.
And then that's the exercises.
What?
Okay.
These
What
are
exercise is
exercises?
that? Yeah,
That's
I might want this exercise. What is this? It's a big one. That's because it's going to be explaining, like, these are the axioms for some field of math or science and explaining what they mean. And then using the axioms to get theorems. So maybe we'll do those next time. Yeah.
8 theorems, that's fun.
And then summaries of rules of inference, and this is just going to give us like a quick table with our different rules and our different restrictions on them.
So basically,
So
nothing
this should
here.
have almost nothing. Yeah, that's the end of it already.
Do you want to go over
So we'll start with chapter 5 next time.
while we have time? Do you want to go over those examples from section 2
Examples from section 2.
that we skipped?
I'm not sure what you're saying, but sure.
He's
We
saying,
started with 4.2.
he's saying the ones that we were supposed to go home and do, but we never did.
Just all the different explanations for like what were the specific things for.
Oh, you're saying go over all the different examples for that they had in 4.2. That's mostly a reading thing. Most of that would be me just writing it up here, what they say, the rule.
I'm saying proving arguments valid, proving premises consistent, and proving axioms independent.
Right, so as they go through that chapter, so they give you everything that you need, and then they go through restating everything that we covered again, giving you one rule at a time.
Right.
So if I did that, I'd have to just write out 7 rules. So that's something I want to do ahead of time because I need to fill out the whiteboard because you'd have to just watch me write a bunch of rules. That's why I'm saying it's just as easy for you to just go read it because I just need me writing up the rule and then explaining the rule and then writing up the next rule and explaining the rule, each rule having a small example to go with it.
Okay.
You see what I mean?
Yeah.
Kind of like we did with the restrictions here.
Right.
So it keeps doing stuff like this. Because I even combined here, there were different restrictions. They give you a restriction, give you the intuition, give you an example using it, then go to the next one. So there's like 7 rules that list out, and I just don't want to write them all out and explain them. But if there's homework problems we want to do, I'm happy to do that.
I didn't bring my homework, but I need someone to do their homework so I can check it.
I should.
I did mine, so I can check it with you.
You did your homework?
Yeah, all of it.
Where's your book?
Oh, I did it in my head. Just barely.
Can I come?
So pull it up and we can do it.
It's what I'm saying is, can I check mine with you?
You can check your homework with me, sure. That's what this time right now would be used for. You say, these are the ones I wasn't sure about, we go over real quick.
Yeah, I kind of want to just like answer key with somebody. Just go over every
Yeah,
problem.
next year you'll have an answer key.
Next year,
You won't teach this, but you'll have an answer key for the book. So.
By the way, with the street math, are you just going to use your old videos?
Yeah,
You
you
might
can
not
upload
upload video
videos.
anymore?
no, I'm going to do new ones and upload my videos and try to get a solid lecture series up there because the first series of videos aren't great. And also, I think that there were times where like the camera cut off in the middle and we didn't notice or weird stuff like that.
Yeah, we
Well,
lost
I
like
think
half an
that's
hour.
always going to
afterwards.
happen.
If you want a solid video series, you're gonna have to do it without the students there.
Well, I don't mean solid as in it's just no bad material all the way through, but now for each class, I can really quick crank through the video, see the things I'm most likely going to screw up in class, make sure I don't screw those up this time, and get something solid.
There was a calculus class. We literally get taught for 13 minutes. Jake asks a question. The next 2 hours, Donnie talking about that. We go on break. Next 20 minutes, we crank some.
Yeah, I have to at least cover what I write on the board. Can't just